right? Viscosity, yes, is related to the friction between the fluids and the pipe surface. So the more viscous the fluid is, you will expect more energy loss, and therefore you need a larger driving force to drive the flow across pipe section. Okay, now we will go back to this viscosity. And this video I have briefly show you during the. This is the video I show you briefly in the in the in the in the lecture, right? And I will also give you this time. I will give you 1 or 2 minutes again, because there is the important equation that we use to calculate viscous force by using a given viscosity coefficient and velocity gradient. Now after that, there will be 2 examples, and the last one is really challenging. So I would like to leave it as a challenge to you today. In the chat room, I have someone. Yes, okay. Some of you are in hotel, and some of you are at home. Never mind. So we try to do it as smooth as possible, right? First, let's look at this video. Now, compressibility is related to gas usually, right? Because gas is more compressible than liquid. Now, in this tutorial, you will see type P because I cannot hear you. That is very difficult, right? So actually, can you hear me? So I now I can type, but it's not so convenient to type everything that I'm going to say. Um, yeah, your internet connection is very bad. So now you will have to video recording afterwards. So at the moment, try the best. Try your best. Okay. The first video is related to compressibility. In this video, right, you will see a gentleman doing a demonstration using a bottle of water. Now, on the top of the water in the bottle, there is air, and he squeezed the bottle, and you will see what happened, right? Okay, let's look at the video first, and then go to the video. Go to the video. The video. Yes, the video is here. Okay. So I need to be hit up again. So no problem. I will be solving it very quickly. Yeah. So how I'm going to do that. Okay. I should be able to share it now. Share the screen. Tutorial 1. Passport. So every time there's something come up, right? Let's see why I cannot share the screen. com. Oh, com. So I have to use com instead of IE. Okay, let's work on this. Com. Okay, I can now share this com. Okay, let's do that. Okay, com. Yeah, I found it. Okay, the first video I'm going to show you is compressibility. So a gentleman will be doing the demonstration and look the change in the gas like above the water. Yeah. No. Let's do it again. Right. Come and then compressibility. Okay, so I think you should be able to see the
demonstration in solids, liquids, and gases, specifically gases. It's a demonstration in air, pressure, air which is a gas. There is gas that remains above the water, filling the space or volume between this red line where the water stops and here where the cap is sealed on the top. This is filled with air, which is a gas. Gases are compressible, more so than liquids and much more so than solids. What I'm going to do next is to tighten this vise, and what's going to happen is the bottle will deform, but also its volume will shrink, the water will creep up past the line, and it will compress the gas towards the top. See the water level rise.
So you see why
past the red line.
Gradually squeezing.
The shape of the bottle is changing underneath.
Water, and you
while the shape
volume
remains
of the air
the same at the top, it becomes pretty obvious that there is the space that the air had occupied, which is a gas, is being taken up by the water. And that can only mean that either the gas is mixing with the water, which it is not, or that the gas is being compressed into a smaller space. Its volume is decreasing. That gas is occupying a much smaller space. And without increasing or decreasing the temperature, that can only mean that there must be an increase in pressure. To check for that, I'm going to try to take this cap off. I'm going to try to do it very quickly for a sudden release of pressure. Here we go.
Interesting, right?
The gas pressure demo showing that a decrease in volume causes an increase in pressure. This time I want you to ask yourself, what causes all that liquid water to be ejected from the bottle in the process? Think about that as you're watching it the second time. Here we go.
Okay, so very interesting things. Okay. Right. Now let's get back to our talk. Okay. So okay, now what you have seen is a demonstration of the compressibility of air, right? Now you will see actually when the bottle is compressed, the volume of the air is reduced, right? So temperature is unchanged, so PV equal to a constant. Okay, now from the equation of state, where PV equal to MRT or NRT or whatever you use, right? The temperature is constant, the mass of the air is constant, the same gas, therefore MRT or NRT will be constant. So P equal PV is a constant at that condition, right? So when we squeeze the bottle, pressure inside the bottle increase and volume of the air is reduced. Now, one thing is, now the gentleman asked you a question. Why the gentleman asked why the water actually is ejects out, right? Come out of the bottle together with the air. Right now, when we compress the whole thing, right, the water and the air. Now pressure in the air increase. At the same time, the pressure in the water also increase. Right now, inside the bottle, because there's no relative movement, so the pressure in the air base is basically the same as that inside the liquid, right? So when we release the bottle, release the cover, the lid of the bottle, the pressurized air come out first, and at that time the pressure of the water is also higher than atmospheric pressure, so the water come out, right? Because of the pressure difference. So now remember, when we compress something, compress the bottle, and the bottle contains air and liquid, the liquid is being compressed at the same time, right? There could be a very small change in the volume of liquid, but right, the pressure inside the liquid is the same as the pressure inside the air, right? Because they are being packed together. Okay, so increase in pressure in both air and liquid. Okay, so far about compressibility, and the first one, and the first example we deal with is the equation of states. So I will go back to this later on after we finish the second video. The second video is viscosity, and actually you watch this video before, but it's good to have a revision and now pay attention to the equation that allow us to calculate the force acting on a moving object inside a viscous fluid. Okay, now we assume here fluids are all viscous. Okay, so no matter it's air, water, they are viscous. But okay, there are only one, I think only one kind of fluid which is really non-viscous, while this fluid is called liquid helium. Um, So this is expensive. We are not going to deal with this. In buildings, we have air and water, oil, gasoline. They are always gas. Okay, let's go to the video again. Video again. It's fun. Everyone's an laminar flow. Stop. Mm. Yeah. Well. So come back to our. Okay, the second video, which you used to have already seen it before. Now I would like you to pay attention to the equations that will be presented in this video, and yeah, he will explain what this equation is all about. Okay, heavy oil is very viscous. Yeah. Oh, sorry, there's no sound from the video. Okay, let's do it again. Okay, so we have a problem. So let's do it again. Let's do it again. Okay. Yes, and this time, I think this time you should be able to hear the sound.
Shear is
Okay,
also
I
confused
think
with the
it's all the way
normal
down.
stress of adhesion, which causes wetting. As we shall soon see, the fact that mercury does not wet the glass stirring rod does not mean that it has no viscosity. Whether a fluid wets a boundary or not, the interaction of the respective molecules is such that there can be no slip either between the fluid and the boundary or between different parts of the fluid. Thus, if one boundary is moved parallel to another, a viscous fluid contained between them will undergo a continuous shear or angular
This layer
deformation,
is not
as
moving, and
delineated
therefore
by
the
the
velocity
velocity
here
gradient.
is zero.
This is known as Couette flow. If we were to measure the force per unit area tau required to move the one boundary or to hold the other stationary, its ratio to the rate of deformation would be a direct indication of the dynamic viscosity mu of the fluid. Lines of hydrogen.
That's enough, right? So we go back to our class. Go back to the PowerPoint. Okay, so in the last, before I stop the second video, you see we have an equations, right? An equations there, by which help us to calculate the let's see, calculate the force, the shear stress, which is equal to mu times something like delta u delta y, something like this. Right, now this is the equation that we use to calculate the viscous force acting on a submerged object moving of a object moving in the viscous fluids. Okay, so we will go back to this equation, very useful equations. Right. So now before we go into the work example, is there any questions? Now, if you have a question later on, then just type. I will try to answer in the classroom. But if the time is running out, if we don't have enough time, then you can through email. You send your question to me through email. Is it equation to find shear stress? Yes, the same equation that we use to find shear stress. I mean the shear stress due to viscous property of the fluids. Okay, viscous stress. It is shear because the velocity of fluids is different. So if you imagine that inside a fluid we have one layer of the fluid moving faster than the other one, then there is a shear. And this equation helps us to calculate the shear stress due to viscosity. Thank you so much for your questions. Now let's do an exercise. The first one is related to the equation of state. Now I'm going to use a whiteboard. Right? Let's do it via the whiteboard facility or backboard here. Okay, whiteboard. So everybody see whiteboard? Yeah. Okay, so yes, I should not go to whiteboard so quickly. I should explain the question first. Well, stop share the whiteboard. Right? And now let's explain what actually you're asked to do. Right, in the first questions, you are asked, you are told that there is a gas. Right, there's a gas, and the molecular weight is 44 gram. Now, molecular weight means the weight of 1 mole of gas. Right, 1 mole of gas. 1 mole of gas contains a particular amount of a fixed amount of molecules. Okay, so the weight is 44 gram. and the pressure of the gas is 0.9 megapascal. Mega means 10 to the power 6, right? Pascal. Temperature of the gas is 20 degrees Celsius, and you are asked to calculate the density of that gas, right, under that condition. Okay, so in order to find the density, you need to find out the volume occupied by 1 mole of the gas, right? Once you got the volume, then you have the mass, and therefore, well, you got the density. And you are given something, and you are given the universal gas constant. So we are going to use an equation of states, which we will use the universal gas constant in the calculation of the volume using our equation of state. Okay, so now let's get to our whiteboard. Whiteboard. Yes, let's practice. Right, this is the first time I'm using this whiteboard, so handwriting may not be that okay. Let's see. Now we have equation of state. Oh yeah, what happened? Well, now density equal to mass divided by volume. Okay, so equation of states is oh shit. Okay, PV equal to NRUT. Now in some situation this is MRT, right? So against no matter it is, no matter you are using N or M, now make sure that you understand what you are using. Now if we are using this notation, then we will be working with the number of mole of the gas together with the universal gas constant, which is a constant for all gas, right? All perfect gas. And if you use these expressions, then M, this here is the mass of the gas, and R is the gas constant, which varies from gas to gas, right? So you can say this R, big R, is a property of a force. Okay. Now because you are given a molar mass, right? So N equal to 1. Of course, M equal to 44 gram or E4 gram, right? Okay, now you are given universal gas constant. So the easiest way to calculate volume, right? To calculate the volume is to use this expression of the equation of state. Now you can use this one, of course, and in that situation you have to calculate the gas constant, which is you take several steps, so extra step to do that. So it's not so convenient. Okay, so we are using these expressions. So PV equal to N. Now the N is 1, while 1 mole of gas, and we have the universal gas constant times the temperature in Kelvin. Okay, you have this, you need to add in 273 to convert the temperature from degree Celsius to degree Kelvin, right? Okay, the density is therefore this number, the volume is these numbers 203 divided by, now the pressure is 0.9 megapascal, so it's 9, 1, 2, 3, 4, 5 Newton per square meter. Now we convert everything into SI unit before we do the calculation, otherwise we will be in trouble. and the volume of the gas is 0.027 cubic meter, right? Let's do some calculations. Yeah, I think so. Times 293 divided by 9944. So it's roughly 200, right? So one more O in between. So 20. So let's write again, right? Is 0.0027 cubic meter. Right, this is the volume. M is, so the remaining work is pretty straightforward. Density is mass divided by volume, and so mass is 0.044 kilogram. Now remember, we convert everything into SI unit before you do the calculation. Otherwise, you will get a wrong answer. Okay, kilogram, right? And then here. The volume is this really small stuff, and the density is about 16.3 kilogram per cubic meter. Okay, and the work is done. Yeah, I like use this word QED here. QED means quite easily done. I learned it from my secondary school. The mathematics teacher like to use this QED. Okay, it's not difficult. Now the question can be asked in many other different ways, right? They may give you the volume, they give you the density, and then ask you to density and pressure, and then ask you to calculate the temperature, right? They can also ask you to. They can also say in this way, right? You are given a density and you are given a temperature, and then you find the pressure. Well, everything basically is kind of relationship between pressure, volume, or density, because we are fixed a mass of gas, right? And the temperature. So PV temperature is what are those related variable in the equation of state. Okay. So any question for this one? Any questions so far? I think my handwriting become better now. I have a morning sections, and the after section it seems that I'm doing quite okay at the moment. Right? So any questions? No, pretty easy. Right? If you have no questions, then we move to the next one, which is viscous force. Okay, second example. Get here. Now let's look at what the question is asking you. Well, here we have two parallel walls, right? They are separated by 25 millimeter, and in between these two walls there is a liquid. There's a liquid, and the absolute viscosity. Yes, the is coefficient of viscosity. Right, it's 0.7 Pascal second. So you have two parallel walls separated by 25 millimeter, and in between there is a viscous fluid, and the viscosity 0.7 Pascal second, and there is a thin plate. Yeah, thin plate, flat plate. Right, there's a missing word here, and the size is this is a square. The size is 250 millimeter by 250 millimeter. Now very thin. And this thing this thing is moving with a velocity 150 millimeter per second, and its distance now it is moving parallel to the wall, to the two walls, and it is at a distance of 6 millimeter from one of the wall. Okay, and now you are asked to assume, which we always does, right? It's always do. Now we usually assume, for simplicity, right? We usually assume the variation of velocity between the plate and the walls are linear, so that the velocity gradient can be easily calculated. It is okay if the separation of the wall is small. Okay, now you are required to determine the force acting on the plate due to viscosity. So here, now let's do it. Right, let's do it. Now to do this kind of question, I will recommend all of you to draw a schematic first. Right. So you have two walls here, parallel walls. Okay, two parallel walls. Now this schematic diagram is very important. First, when you become better in understanding the question if you can draw the correct schematic. And it's in the answer book, right? In the future, when you are doing questions, now we can the assessor can look at your schematic diagram and understand how far you understand the problem. Okay, so now remember to do that, right? We have plates moving in the inside the fluids, with a velocity, with a velocity, what was it? Velocity, which is 150, 150 millimeter per second, right? And it is, yes, right? 6 millimeter from one wall, and the separation between the two wall is 25 millimeter. Okay. Yes, this is the schematic. Now you are asked to assume the velocity gradient between between the plate and the wall is linear. Okay. And now, because this wall is not moving, so the velocity at the wall is 0. So now we draw the velocity profile. Right? Velocity profile is simple. Right. The velocity also. What's that? Right. Now the velocity at the location of the object is that, right? Suppose we use the symbol V, and this is Y. So now this, okay, this is our velocity profile. This is our velocity profile. The red line is our velocity profile. Okay, our velocity profile. So at the wall, it is 0. Velocity is 0. At the wall, velocity is 0, right? The wall velocity is 0. And the velocity is very linearly with distance from the plate. Okay. So we have a velocity profile like that. The velocity gradient is easy, right? We just the differential velocity is v minus 0, so it's v, and the distance between the plate and the wall is y. So the velocity gradient, this gradient is just v divided by y. Now there are two sides of the plate, right? So we have a viscous stress on the upper side of the plate and also on the bottom side of the plate. So now we will consider the bottom first, right? Bottom first. Bottom side of the plate. We use our equation tau equal to mu times velocity gradient, right? Velocity gradient, and this time it's really simple. It's mu v divided by y, and you understand, mu is 0.7 here, and you are given the velocity is 150 millimeter, and y is 6, right? So here we have this viscous stress is somewhat like this, which is 70.5 Newton per square meter. Okay, so far so good. Now it's really not so difficult, right? Okay, this is lower side. Right, we have the stress equal to mu and the velocity gradient, and this time is simple, right? V minus 0, V minus 0 give you V divided by the separation, right, which is for the bottom one. For the bottom side, the separation between this plate and the bottom plate is 6. So you have this simple. No. I missed out something here. Yes. Is some sort like 150, right? Okay. So the bottom side is finished. Now let's look at the upper side.
OBS Studio 係啊
Upper side
係啊，可以錄自己揀好多嘢。我而家錄緊呢一頁咯。
upper side. The upper side.
咁我呢個畫面應該睇住呢度啦。咩啊？
Very bad.
如果咪碌柒咯，
Upper side.
碌柒㗎啦。
Let's draw out the upper side. We have the places here.
撳咩啊？呢個咩撳入去啊
So upper side, the distance here is 25 minus 6, right? Velocity v, velocity here is v equals 0. So
佢哋都有話自己嘢啊，真係好啦，戇鳩。
喂 tau, the shear stress due to the viscous stress, right? Is mu times velocity v again, right? Because v minus 0 you can write, but it's v, right?
會啊。
And downstairs here in the denominator is the distance 25 minus 6.
飛住嚟睇就係睇自己想睇嗰啲啦，仲使問嘅。
So 0.7 multiplied to 150 millimeter divided by 19. So who can? Let's do some calculations. My calculations.
你想點啊？
0.7 times 100,
公開喎，但係
0.7 times 150 divided by 19 mm, which is
我都冇
about
話啦，
here
自己睇啫嘛。
5.5
但有營收啊嘛。
5.52.
俾完錢交學費，梗係要由佢哋身上拎翻去喎。
Right? 5.526 Newton per square meter. Okay, now we have the upper stress and the lower stress. So the next thing is pretty straightforward now, which is the force, right? The force
呢
equal
個流體力學嘅 shear strength
okay. The force equal to
shear
the force right? The force
唔
equal
係 stress
to
係
now we have upper stress, right?
shear 咪
Upper
剪咯，
stress
直接咪剪咯，
and
佢係
then
咪
the
剪
bottom
咯？
stress,
剪係咩分點啊？
right?
剪鉸剪嘅
And
鉸剪
multiplied to the area,
交叉
surface area of the plate,
食翻四心
right? So upper
something.
stress is
You
17.5,
motherfucker!
right? Lower stress is sorry, it's the other way around, right? Okay. It's the other way.
掟咗俾你嘅喎。
The upper stress is 5.526 and the bottom stress is like that. Now area, well area is 250
望到個樣都唔可以揾得行開
millimeter
啦
times
你。
250 millimeter. Now remember, right, we have to convert this dimension
嗱呢個
into
OK 啊
SI unit. So the area is 0.25
鬼極
times
知
0.25
唔啱其實，我唔
meter.
中意睇呢啲。
無限發射篇咯。
Right? Now we have to convert everything into the same unit before we can do a calculation, right?
啱嘛？
Now the stress is given in Newton per square meter, so area has to be in the unit square meter.
send 咗圖俾
Okay, 250 millimeter is equal to 0.25 per meter. Okay,
結
so
果可能
all
就因為
together
條你
要
嗰
翻
條你就俾你
the
KO 咗
answer
喎。
但係佢依家
given in the tutorial sheet.
我撚知啊！你唔問佢，記得啦，我唔想知嘅，其實我冇咁八卦㗎，你班撚樣。
So now there are also so many different ways the question can be
所以
asked,
我
right?
想講，我唔想
The
知
answer can be
㗎，
said.
救命！
Right, one thing is I give you the surface area
你
of
聽
the
晒佢咪得
of
咯
the？page, and then I give you its velocity, and you are required to find out the location of the plate, right? And also I give you the force, I can give you the viscosity, I give you where the
其實
the plate is moving, and then you ask to calculate the area of the surface area of that tiny flat plate. So this time, this question is quite straightforward. Okay. Now remember, this time we have two walls, and therefore, and the object is moving in between the wall. So we have two stress, right? One on the upper side of the plate, and the other on the bottom side of the plate. So we have two gradient to calculate and two stress to find, and afterwards we just add them up and then multiply the stress to the total stress, right, to the area of that plate. Okay. So any questions so far? Now I'm going to post up some revision question for you via Badboard. I am trying to do that before the start of this class. I have finished typing, and the next thing I will do is to upload that kind of revision MCQ onto Badboard. So I hope that today or tomorrow you will receive my announcement. And those are just a very simple kind of revision. I hope that those things can strengthen your concept related to properties of fluids, the gauge pressure, and viscosity. Okay. So this is the second example. Okay. Next, we go back to our file, our tutorial sheet. Now the last thing is, I understand we are about time, right? But anyway, I would yes, like to talk about this question, but of course I'm not going to do it in front of you. Now this is left to your challenge. Okay. Now here we have two discs, right? And in between the two discs, coaxial discs, right? It means that they have the same axis. Right? These two discs, in between these two discs, there is a oil, right? A film oil as lubricant, something like that, right? It's very common. It's a very common problem. Right? And the two plates are separated by very small separations. Well, and the viscosity of the oil is 0.14 Pascal seconds, and you are given a diameter of the disc, right? And then, most importantly, the two discs are not rotating at the same speed. Why one disc is moving faster than the other, and the relative rotational speed is 7 revolutions per second. Okay, and you are required to find out the top necessary to rotate one disc, right? To rotate the disc. Now, actually, the actual reaction, right? The torque acting on the faster disc is equal to, but of course in opposite side, right? Is basically equal to the torque acting on the slower disc. Of course, the side of the torque are different. Okay. So this is a very challenging question because you understand in a this like this, right? You have center, right? The velocity at a distance r is given by, suppose we have a rotational speed omega here, right? The velocity is equal to r omega. Therefore, the velocity, the linear velocity, actually vary from place to place on the disc. Okay, so if you work our cross section like this, right? Then the velocity here, the velocity here, the velocity here are not the same. So you have closer to the disc, the velocity is lower, and the velocity profile can be like this. Right? Further away, suppose this is the axis, right? And further away, the velocity gradient can be like that, and then further away, the gradient can be that large. So you have a very non-uniform stress on the disc, right? And the top, and the top, and the top is summation on all the force time out, right? So what you are going to do is to find the stress on the disc, multiply by that small area, and you sum up all these torque, right? Once you have the force, you have force times the R radius equal to the torque, and so you sum up all the torques, right? And then you find the total torque. Now it is not so simple, and you understand, right? This kind of integration basically can be done using calculus, right? Integration, something like that. What is inside? So I will leave you to this as a challenge to you. Right? Of course, I will give you the answer, but not this week or next week. No, right? I'll give you some time, so that you can, try to work it out. Now, well, you are told that the two discs are not rotating at the same speed, and you are given this velocity, angular velocity. So you can actually treat one of these as a stationary disc, and the other one is moving with an angular velocity of 7 revolutions per second. Right? Okay. So that is this will be your challenge. Now give you 1 or 2 weeks to do that. Now, I think this is what I have prepared for this tutorial. Do you have any questions? Far so good? Yeah. Anyone? No questions? So good? Very good. Thank you so much. Do you understand? I hope you understand why this part of the calculation is not so difficult, right? Now the question is equation of state, right? The first thing you need to understand and be able to apply is the equation of state, PV equal to MRT or PV equal to NRUT or something like that. Then is how to calculate the viscous stress. With the video of this lesson be uploaded to the YouTube soon. Now the video recording can be uploaded to YouTube or I will give you a link so that you can watch it via better. So either will do. Now last time I make this on YouTube because I want to edit out some very bad things during the classroom. Right, and I think this time we got a more experience, and therefore I think I tend to give you a link so that you can go to give you a link, not in YouTube but on Bedbot, right? The same basically. You will find it's usually the video will come out. It depends on how long your video is, right? This one is about 650 something minutes, so we will come out about 1 hour's time, and after that I will watch the video and see is there any bad things happening. If there is if the video is acceptable, then I will give you the link. And I told you that I'm doing some revision MCQ for you. So after this class, I will try to upload the MCQ onto Bedboard, and I will give you an announcement for all of this. I hope before I leave for you today. What exactly coaxial mean? Now, coaxial means now you have two things, right? Coaxial means they have the same axis, so they are rotating about the same axis. Is it okay? Do this at the same axis. So they're just moving slightly above each other. Now let's see who actually can finish this challenge example. Now if you can finish it, and I hope that you can write it up and then post it to me via email. And if you don't mind, I just post your working. Of course, I'll keep you anonymous, right? On Bedbot. I got a question from previous section. Oh, okay. May you explain again why pressure is not a property of fluids? Well, now in the polling Word document, I explained already. Now pressure. Why? What is the properties of a fluid? Now, if there is no change in the fluid, then the properties should not be changed, right? Should not change. Now, for pressure, it is not a property. But for example, if you dive into water, yeah, I hear my voice. If you dive in the water, now the temperature is unchanged, water is unchanged. So suddenly the pressure in the water when you dive down into the water, the deeper you go, the stronger the pressure that will be acting on you. So pressure is not a property of fluids. Understand? Now the property of fluids is if we have the same fluid, same condition, the property is constant. And we assume that they are placed parallel. What do you mean? Parallel. I mean you go back to the dates, right? Martina, you are talking about the dates, right? Two dates. Yes, they are parallel. The two dates are parallel. But it doesn't mean that they are coaxial. Right? The coaxial means they have the same axis. A this and the axis is like that. A this here, I have this, and the axis is this axis. Okay, if you have further question, I will be still in the classroom, and this section will be closed at 5:45. Right? For those